Hello, viewers. All right, 3 people are on time. Awesome. Gonna wait a little bit longer for the number of viewers to increase. Oh. Oh man, people are slow to roll in today. All right, I'm up over 20 viewers, so I'm going to go ahead and get started. Hello, everyone. Happy Friday. Mr. Pettibone here. This is AP Physics 1, September 25th, period 6. All right, let's go. Today we are going to be talking about what is called projectile motion. Projectile motion is two-dimensional motion under the influence of gravity. Two-dimensional motion under the influence of gravity. So technically speaking, what we did in the last lesson with doing kinematics problems where things were accelerating due to gravity, that was technically projectile motion. But today we're going to really focus on the two-dimensional aspect of it. Okay, so let me show you the kinds of problems that we'll learn how to solve in the next 2 lessons. You have a cliff. The cliff has a certain height, maybe it has a height h, and we launch a projectile off of the cliff. So the projectile has an initial launch speed, v0, and it has an initial launch angle, theta. Okay? And so the projectile is going to fly through the air diagonally in a two-dimensional arc. Okay, so notice how the velocity does not stay. Whatever velocity you launch the projectile at, that's not going to be the velocity that it stays at, because the projectile is changing directions as it travels. It's changing speeds as it travels. And so we're going to answer some questions like, how much time is the projectile in the air for? How far horizontally does it go? How high does it go? Things of that nature, okay? We are going to be neglecting air resistance. So the answers that we get are only going to be approximations, sort of ballpark numbers, at least on Earth. If we were to use these equations that I'll show you today on the moon, they would be extremely accurate because the moon has no atmosphere, okay? All right. So the first step in learning how to solve two-dimensional motion problems is learning how to deal with two-dimensional velocities. So dealing with two-dimensional velocities. Okay. So when I say a two-dimensional velocity, I mean a velocity that is sort of at an angle. Okay. And if the velocity is at an angle, it has a certain launch angle, which I'll call theta. And it has a certain launch speed, which I will call v naught. So this is the launch speed. Now remember, this is only the speed at launch. That the angle is going to change as the projectile flies, and the speed is going to change as the projectile flies. So this is only at the beginning of the problem, just after launch. Okay. All right. So it turns out that a diagonal velocity can be thought of as a vertical velocity and a horizontal velocity. Okay. If you're moving diagonally, your diagonal motion is simultaneously moving horizontally and vertically. Okay. So what we want to do is we want to figure out, if you have a diagonal velocity, how much of that velocity is vertical and how much of that velocity is horizontal. And it turns out that it obeys the laws of trigonometry. So we basically just make a right triangle out of the velocity. And the vertical leg of this triangle I will call v sub y naught. So so this is the y component of the velocity, of the initial velocity. Okay. And it's just, and then we have vx naught, which is the initial horizontal component of the velocity. So the x component of the velocity. So component basically means the leg of the triangle, the corresponding leg of this right triangle. The launch speed you can think of as the hypotenuse. Okay? So so we're going to do some trigonometry to get the legs of the triangle. Okay? So if we look at the horizontal leg here, the horizontal leg is right next to the angle. It's adjacent to the angle. And if you remember your trigonometry, the trig function with adjacent in it is cosine. Cosine is adjacent over hypotenuse. So the formula for the x component of the velocity is going to be v naught cosine of theta. Okay? The y component of the velocity, if we look at the vertical leg of this triangle, it is opposite the angle. Okay? The trig function with opposite in it is sine. Sine is opposite over hypotenuse. So that means that the y component is v naught sine of theta. Okay? So if we have a launch that is diagonal, we can turn that into a vertical motion combined with a horizontal motion. Okay? So let's show how that works with a concrete example with numbers. let's suppose that I launch a projectile at 90 meters per second at an angle of 65 degrees above the horizontal. Okay? So if I want the vertical component of the velocity, it would be 90 sine of 65 degrees. You want your calculator to be in degree mode for this lesson because I gave you the angle in degrees. Okay? So my calculator is already in degree mode. I type in 90 sine of 65, and I get about 82 meters per second. I'm rounding because I don't have to be within 2%, like you guys do when you do the homework. 82 meters per second. So there's a question that why is sine of theta multiplied by the initial velocity? That's a really good question. So I'm going to answer it up here. So basically, if we look at this, opposite over hypotenuse would be Vy naught over V naught. So sine is opposite over hypotenuse. And if we look at opposite is Vy naught. And hypotenuse is just V naught. So Vy naught over V naught equals sine of theta. And then you multiply both sides by V naught, and you get V naught sine of theta equals Vy naught. Okay? So so basically that's the hypotenuse that you're multiplying through. Okay. That's a good question. So the horizontal part of this velocity is going to be 90 times cosine of 65 degrees. So if I plug that into my calculator, 90 times cosine of 65 is about 38 meters per second. By the way, this I've drawn it more like a 45-degree angle of launch. It should be more vertical than I drew it. I don't know why. So what that means is that if you launch something with a 90 meter per second speed at an angle of 65 degrees above the horizontal, it is equivalent to moving up and down at 82 meters per second and to the right at 38 meters per second simultaneously. Okay? Let's talk about a couple of special cases. So one special case is a horizontal launch. Oh, thank you. Horizontal launch. So a horizontal launch means your initial velocity looks like this. Okay. You have a vertical launch where the initial velocity looks like that. Or you could have a sort of exactly diagonal launch that looks like that. Or you could have some other launch angle, but these are just some special cases. So what would be the launch angle in each of these cases? Type it into the live chat if you know what is the launch angle in each of these cases. And while I wait for someone to type in what they think the answer is, I will start the next part, which is equations of projectile motion. Excellent. So yeah, some people are So horizontal launch means that the launch angle is 0 degrees. Vertical launch means that the launch angle is 90 degrees. So what is special about a horizontal launch? Well, a horizontal launch has all of the initial velocity is horizontal and none is vertical. So that means that if you launch something horizontally, Vy naught equals 0 because the initial y part of the velocity is not present. With a vertical launch, all of the velocity is vertical. So you have that Vx naught equals 0. None of it is horizontal. All of it is vertical. If you have a diagonal launch, that is correct that it is 45 degrees. And the significance of a 45-degree launch is that it's equally vertical and horizontal. Okay. Here we could see that 65 degrees is closer to vertical than it is to horizontal. So it's going to have a bigger x or y component of the velocity than its x component. Okay. All right, so we're going to learn the equations of projectile motion now. There's two of them, and they are both based on the first kinematics equation. This was the first kinematics equation. Okay, so we are going to have an equation for delta y, and we're going to have an equation for delta x. So the delta y equation is v y naught times time minus 1/2 g t squared. Okay, so notice the similarity in structure to the first kinematics equation. Okay, what are the differences? Well, it's delta y in terms of delta x because that's describing vertical motion. Instead of v naught, this is two-dimensional motion. So instead of the initial velocity, we only worry about, for the vertical motion, we only worry about the y component of the initial velocity. So see how that's Vy naught. So that would be the Vy naught. If it was a 90-degree launch at 65, or 90 meter per second launch at 65 degrees, then this number would be 82. All right. And then we can see we have a minus 1/2 g. So that means that the acceleration is negative g, which is another way of saying negative 10 meters per second squared. All right. Our delta x equation is Vx naught times time. Notice that the delta y equation has a t squared term, but the delta x equation does not have a t squared term. Okay? Why is that? Well, that's because gravity causes things to accelerate vertically. Gravity doesn't pull things sideways. Okay? So the t squared term represents acceleration. Gravity only accelerates things vertically. So we only have a t squared term in the delta y equation. We don't have it in the delta x equation. So these two equations are the equations of projectile motion. Okay? And we can use them to calculate these types of problems. All right? So let's do some examples. We're going to do 3 examples today. The first example is what I like to call horizontal launch off a cliff. So it's horizontal launch. That means that the angle of launch is 0 degrees, just like you said, okay? That means all of the initial velocity is horizontal, none of it is vertical, okay? So I'm just going to draw a picture of the problem instead of writing out everything, because I think, you know, picture's worth 1,000 words, so you should be able to figure this out. So here's a cliff. The cliff is 120 meters tall, okay? And you are at the edge of the cliff, okay? And you just got dumped by your significant other, okay? And your significant other made a mixtape for you of all the songs that reminded your significant other of you, and they gave that mixtape to you. And you cherished that mixtape while you were together, but now you got dumped and you're beside yourself, and so you're like, well, what do I do with this mixtape? You go to the edge of the cliff and you throw the mixtape off the edge of the cliff horizontally. So here's the mixtape. You don't want it anymore. You're moving on. There's the mixtape. You threw it horizontally at 45 meters per second. Now the mixtape is going to undergo a curved arc. It's going to hit the ground. It's going to shatter into 1,000,000 pieces. And that's going to be very satisfying to you. It's going to help you move on. And what we would like to calculate is how far horizontally does this mixtape go before hitting the ground. Okay? So there you have it. So I'm going to start out with my two equations of projectile motion. I have a delta x equation, which is Vx naught times time. And then I have a delta y equation, which is Vy naught times time minus 1/2 gt squared. Okay? So what is Vy naught in this problem? Well, because it is a horizontal launch, none of the initial velocity is vertical. So Vy naught is 0. All we have is this second term because it was a horizontal launch, not a vertical launch. So 1/2 g, negative 1/2 g is negative 5. So we have negative 5t squared equals delta y. That's our delta y equation. Our delta x equation, all of the initial motion is horizontal. So Vx naught is the full 45 meters per second. So we have delta x equals 45t. So these are our two equations. With these two equations, we can solve everything we need to know about projectile motion. But we do need one additional piece of information here. So if I consider this to be my starting point and the ground to be my ending point, we can see that the mixtape dropped 120 meters. Okay? So what is the mathematical statement? Okay, while I type it into the live chat if you know, what is the mathematical statement of saying that the mixtape drops 120 meters, okay? And while I'm waiting for someone to answer, I'm going to answer the question in the live chat. So negative 1/2 g. Well, g is the acceleration due to gravity, which is 10 meters per second squared. So we have negative 1/2 of 10, which is negative 5. Okay? So this term is just negative 5. Someone typed in a vertical displacement of 120 meters. That's almost right. Delta y. So delta y is equal to, who can correct the, there's just a minor adjustment just saying that delta y is 120 meters. It drops 120 meters. Very good, yeah. So the vertical displacement is negative 120 meters because it drops. So I'm going to take that and I'm going to plug it in for delta y here, negative 120. Notice what would happen if we didn't have the delta y being negative 120. Then, when we solve this, we would divide by negative 5, okay? And then we would have negative 24, and we would have to take the square root of that. So we would have the time elapsed would be an imaginary number because we're trying to take the square root. So we need two negatives here so that they cancel out and we can actually take the square root of a positive number, okay? So again, dividing both sides by negative 5, the negatives cancel out, and I get 24 equals t squared, okay? And then that means that t equals square root of 24, which is about 4.9 seconds. Yeah. Okay. 4.9 seconds was the time of flight, which I then plug into my delta x equation, and that's going to give me my final answer. So 45 times 4.9 gives 221 meters per second. Or meters, not meters per second. All right. So that's how far horizontally the mixtape goes before hitting the ground and fragmenting into a bajillion pieces, and it's very satisfying for you. Okay? I want to talk about just sort of a good strategy for projectile motion problems. What you want to do, generally speaking, is you want to find the time of flight from one equation, either the delta y equation or the delta x equation. And in this case, because of the way that the problem was described, delta y is negative 120 meters, so we had to use the delta y equation. Find the time of flight from one of the equations, and then we use that time in the second equation. Okay? So that's, generally speaking, a pretty good way to solve projectile motion problems. Okay, let's do another example. I'm going to call this diagonal launch across a level surface. Okay, so let me draw. So the example that comes to mind is the military snipers. So here's a level surface. Okay. Here's the sniper rifle. There's the sniper. It's laying on the ground. Like that. And the sniper launches a projectile at 500 meters per second. Okay? Does that mean the velocity is always going to be 500 meters per second? No, that's the initial launch speed. Gravity will accelerate the bullet, cause it to curve, cause it to speed up, slow down. So the direction and size of the velocity will be changing. And it's launched at an angle of 10 degrees. Okay? So the projectile goes in this arc like this. It lands over here. We want to know how far does the bullet go. Okay? So anytime we have a diagonal launch, we want to start off by creating our initial velocity triangle. Okay? So our initial velocity triangle kind of looks like this. So do the trigonometry first, I would recommend. So we have 500 meters per second is the launch speed, and the launch angle is 10 degrees above the horizontal. So the vertical component would be 500 sine of 10 degrees, which is about 87 meters per second. Okay, the horizontal component of the velocity would be 500 cosine of 10 degrees, which is about 492 meters per second. So launching something at 500 meters per second at an angle of 10 degrees is equivalent to moving upward at 87 meters per second and sideways at 492 meters per second. Okay. Notice that to get, so for example, if I had calculated this first, 492 meters per second, I can't get the other component by just subtracting this from 500. No. You have to do the trigonometry. Okay? Notice how these two velocities add up to more than 500. It's just the way it works. Okay? So now I go to my delta x equation and my delta y equation. My delta y equation is v, exactly, Pythagorean theorem is how you would, 87 squared plus 492 squared equals 500 squared. So Vy naught is 87. So I have 87t. And then negative 1/2 g is, again, negative 5t squared. So that's my delta y equation. Vx naught is 492. So I have 492t. These are my two equations here. All right? Now, I need another mathematical condition to solve the problem because this has 3 variables. That's one too many. So the bullet starts and ends at the same elevation. So who can tell me? This is similar to the chicken wing problem. What is a mathematical statement that represents the that we start and we end at the same elevation? And while I'm waiting for an answer, did you know you can type a delta by saying Alt-J? Alt-J is another way of typing delta. It's kind of nice. So you could actually say Alt-J-Y. Okay. Exactly right. So because it starts and it stops at the same elevation, we are going to have that delta y equals 0, just like the chicken wing problem. Okay? And that comes from the fact that this is a level surface. If it was a sloped surface, we could not use that condition. We learned how to handle sloped surfaces in my AP Physics C class. Okay, so I'm going to plug in delta y equals 0. Okay, I'm going to add 5t squared to the other side. 5t squared equals 87t. Divide both sides by 5. 87 divided by 5 is 17.4. And then, again, time is not equal to 0 because it takes a finite amount of time for the bullet to travel. So I divide both sides by t, and I get that the time of flight is 17.4 seconds. Okay? So then what I want to do is I want to plug that into my delta x equation. I'm using my good strategy here. Okay, find the time of flight from one equation, use that time in the second equation. So my horizontal displacement is 492 times 17.4. And that's about 8,561 meters is our delta x. Okay, I want to stress for this one that's really an approximation. Okay, because now what makes something very susceptible to air resistance? Something is susceptible to air resistance if it's moving very fast, which a bullet is, and if it's very light, which a bullet is. It's not bullets aren't very heavy. So that means that the bullet is easily pushed around by the wind because it's light, and because it's traveling at 500 meters per second, there's a lot of wind. Okay, so this is a pretty rough approximation in this case. But it would be incredibly accurate if you had a, this would be incredibly accurate if you had no atmosphere. Okay? We're going to do one more example. Let's see. How would the spiral of the bullet affect that? Yeah, so as you know, rifles have rifling, which is kind of like a spiral groove that is in the tube, the barrel of the rifle has these spiral grooves in it that impart a rotation on the bullet. Okay, now if you have a bullet that is rotating, it is stable. Okay, think about when a football player throws a spiral. That spiral ensures that the football points in a consistent direction. Okay, if you don't throw a spiral, if you don't impart spin, then the football can tumble. It can do all kinds of things. Same thing with a bullet. If you don't put the rifling in the barrel, the bullet won't spin, and it'll be stable, and it could tumble, unstable, and it could tumble end over end, which basically what you're trying to do is you're trying to get the most aerodynamic direction of the bullet to be pointed forward. Okay, so the bullet is going to fly a lot more consistently with the rifling. Okay, that's an interesting question though. So all that has to do with air resistance. If you had no air resistance, you don't need the rifling. It's just going to go the same way every time. Okay. Our last example for today. In the example above, how high does the bullet go? Okay? How high does the bullet go? So basically what I'm asking is, what is delta y right here? Okay? So the key idea for this problem if the entire time of flight is 17.4 seconds, this is a symmetrical arc that the bullet is going in. Okay, so here's 0 seconds when it's launched. Here's 17.4 seconds. So at what time do you think it's going to reach the highest point? Type it into the live chat if you know the answer. And while I'm waiting for the answer, the highest point is reached okay, so yeah, people are typing in half, the midpoint, yeah. So if the entire flight was 17.4 seconds, then we're going to reach the highest point halfway. All right, so that would be 17.4 over 2, which is what, 8.7 seconds. So the highest point is reached 8.7 seconds into the journey. So I'm going to take my delta y equation and I'm going to reuse it. Okay? This equation is true throughout the motion. All right? So I can reuse this equation. All right? But I'm not going to plug in 17.4 seconds. I'm going to plug in 8.7 seconds. So I have 87 times 8.7 minus 5 times 8.7 squared. And that gives that the maximum altitude of the bullet is 378 meters per second. And that's our answer. Okay? I want to stress, though, that you need to be careful when you divide it by 2. The fact that I divided the time by 2 was a reflection of the fact that this trajectory is symmetrical. Okay? If I look at the mixtape problem, oops. Thank you. Yeah, you're right. That should say meters. 378 meters. Good catch. Thank you. So because the arc was symmetrical, I could say that the highest point is halfway. If you have an unsymmetrical arc like this, if you think about this, this is only half a parabola. When is the highest point of this one, the mixtape problem? Well, the highest point would be at time 0 when it was thrown. Okay? Because gravity immediately starts to pull it down. Okay? So you can only use that the highest point is reached halfway if it's this symmetrical arc across a level surface. In the next lesson, we'll learn how to handle the general case. All right, so that's my lesson for today, and I hope you enjoyed, and I will see you in the Zoom room in just a minute.